So hello everyone, welcome back to Math 140 Business. We are now in Thursday of week 14, which means a week from today we are done with the semester, other than the final, of course. And today we are going to be doing chapter 6. So I'm going to share my screen here. Share contents. And here we go. Chapter 6, probably the easiest chapter in the book. And the only reason we're doing it is because we need it to do chapter 24. In fact, if you look at page 153, which is chapter 6, there's an asterisk by it. And it said, this material is important in statistics, but it is needed later in this book only for chapter 24, which is why we're doing it now. So two-way tables, very straightforward idea, and best illustrated in the form of an example. So we have on page 154, if you have the book at home and you're following along, the following diagram. We have women, no college, women, yes college, men, no college, and men, yes college. That is one categorical variable. And then we have outside job, outside of home job. I'm paraphrasing here. Outside job, inside job, like taking care of the family and taking care of the house, etc., or don't care. And this is the preferred lifestyle variable, lifestyle. So for preferred lifestyle, that's one category. There are three options. Either I prefer to have a job outside the house, I prefer to have my job being inside the house as a caretaker and situation, or no preference at all. And the other category is sex and education. Whether you have women with no college, women with college, men with no college, men with college. And we have the following data. 81 people fall in this category, 173 fall in this category, 92 people fall in this category, and 299. Then we have 104 and 115 and 32 and 81. And then we have 10 and 15 and 2, and then we have 8. So these are the data, and this is a group of a total of 1,012 individuals. And we don't really care so much if it was a survey or if it was an SRS. Let's just assume that it's a valid and representative collection of data. So what we have here are a few things. One is what's called a joint distribution. We know that a distribution in general is possible outcomes together with their likelihoods. A joint distribution is when you have two or more variables. In this class, it's just going to be two. So two variables linked so that the outcomes are not just outcomes for one variable at a time, like we've done until now, but rather two variables together. So I might say something like, what is, for example, what is the probability that a woman with no college wants to have an inside job? Ran out of room here. What's the probability that a woman with no college is also someone who prefers to have an inside job? The third column is don't care. In other words, people say, I don't know, whatever. Inside, outside makes no difference to me. I don't care. So what is the probability that a woman with no college wants to have an inside job? As a fraction, what would that be?
115 over 1012.
I agree with the 112, 10, 12. But where's the 115 coming from?
Women, yes. Inside job.
But I'm asking for women, no inside job.
Oh, you said women, no.
104?
Sorry, 104.
Okay,
Yeah.
so 104 over 112, whatever, that's about 10%. The likelihood that a woman with no college wants, that I pick at random, a woman who with no college education that prefers to have an inside job is roughly 10%. That's a joint distribution because the only way to calculate it is to combine two variables together at the same time jointly. But what if I ask the following question? What's the probability that a woman, that I just pick a woman with no college? What would that be? So how would I compute such a thing? What's the likelihood that I pick at random a woman who has no college education?
Wouldn't you just add all three of the women no and then put that over 1012?
That's exactly what I would do. And the book is actually very nice. It gives me these. I didn't want to put them until I needed them, but it gives me the totals here. Of course, I could have computed them, without a calculator. I could just add them together, but it's easier when they're given to you. And therefore, what is the probability that I pick at random a woman with no college education in this study?
195.
195. Is that your answer?
Yes.
Just 195? That's the likelihood that I pick one?
Over, well, you already have the denominator.
Oh, so I see what you're doing there. Okay, all right, 195 over 1012. Now notice, to calculate that, I didn't actually look at the inside table. I just looked at the margin. Agreed?
Agreed.
Yes.
So to do that, we have what is called a marginal distribution. The marginal distribution is just using the numbers in the margins without actually considering the data for each cell. All I care about are the ones in the margins. Now, in this case, I only have one joint distribution. It's the table. But how many marginal distributions do I have in this particular example?
4.
I'm sorry?
4.
I don't have 4.
Is it 2?
I don't have 2.
3.
16.
I don't have
Is
6.
it 12?
Not 12.
Is it some number?
It is some number.
7?
7. What is 7 from?
Woman no, woman yes, man no, man yes, outside job, inside job, don't care.
That's right. Every one of those red numbers is its own marginal
Bingo.
distribution. Well, actually, my apologies. I was thinking in my head something different. It is 2. Someone did say 2. So my apologies. I know someone said it right off the bat. I said no. I was thinking of something else. I'm sorry. The 2 marginal distributions are sex and education, which are these 4 numbers. That's one distribution, and the other one is preferred lifestyle. That's the second one. Again, I'm sorry. So there's 2 marginal distributions. There's the first categorical variable, which has 4 possibilities. And if you add up the 4 possibilities, it adds to 100%. And then the second one is the preferred lifestyle distribution that has 3 possibilities. And if you add up those 3, it also adds to 100%. So the number of outcomes is 7, but again, it's 4 for this distribution and it's 3 for this distribution. So I initially said it wrong, but did that clear up what I was referring to? Does that make sense?
Yeah.
Okay, so there's one joint and there's 2 marginal distributions. Because remember, for the joint one has one joint distribution, has a total of 12 numbers. And when I add up all 12%, if I convert that to percents, it has to add to 100%. For the marginal ones, there's 2. There's one on the right and there's one on the bottom in the margins. And they each have to add to 100%. But I actually have a third type of distribution. And this is the most important one, I think. It's called the conditional distribution. For example, what's the probability that a person wants an inside job given that they are a man with education? What is the probability? I'm not even telling you how to calculate this. I want to see if you can intuitively get it. What is the probability that a person wants to have an inside job given that they are a man with college education? What would the fraction be for this one?
Would it be 81 over the amount of men in the study?
So 81 over what?
The amount of men in the study?
Not the amount of men in the study, no.
The inside job, 332.
It is not 332.
338?
3, how much?
388.
388 is correct. See, this is the given, right? We are assuming that the person under consideration is a man with college education, which means the only thing we care about for this particular example is that row. Nothing else matters for this problem. If we know for a fact that we are dealing with a man with education, then that's the row that it's the only row that matters. That's the man education row. And then given that we're in that row, if I want the likelihood of somebody wanting an inside the house job, well, 81 of those 388 people want that job. Does that make sense?
Yes.
So how many conditional distributions are there in this problem? We know there's one joint and 2 marginals for this particular problem. How many conditional distributions are there? Different conditional distributions are there for this problem?
Would it be 4?
It would not be 4.
8? Oh no, 7?
This one is 7. Anahid, excellent. This one is 7 because you can condition on 7 different things. You can condition on a woman with no college education, and there's 3 possible outcomes, and the percents have to add to 100%. You can condition on the second row, or the third row, or the fourth row, or the first column, or the second column, or the third column. So in general, there are going to be more conditional distributions than there are marginal distributions, and therefore more than the joint distribution. You're always going to have one joint and 2 marginals, assuming it's a 2-dimensional situation. I mean, in theory, I can have a scenario that would be hard to visualize that might have more than 2 variables. I can list them in tables, but I can't really visualize a 4 or 5 or 10-dimensional, box. It's just not something that the human mind is capable of doing. We can go 2, we can imagine 3, but we can't go any higher. But I can write all the information down if I really wanted to. In this class, it's always going to be two-way tables. That's the name of the chapter, two-way tables. 2 categorical variables, one for this way, one for this way. In this case, we have 7 conditional distributions depending upon what you condition. Are there any questions on that? The difference between a joint distribution, a marginal distribution, and a conditional distribution. Does that make sense so far?
Yes.
Okay. So now we're going to end the chapter with the idea of Simpsons Paradox, named after the eminent mathematician Homer Simpson. And we have the following example. It says here, accident victims are sometimes taken by helicopter from the accident scene to a hospital. Helicopters save time. Do they also save lives? Let's look at the following table. We have died and lived. We have went by helicopter or by road. And this is the data that we have. So this is my two-way table. Died, went by helo or by road. So what I have here is the joint distribution of both variables. How many people died altogether in this study?
324.
324. How many people lived altogether in this study?
976.
976. How many people went by helicopter in this study?
200.
200. How many people went by road in this study?
1100.
900.
800.
Oh, sorry, no.
And therefore, how many people overall were in this study?
$1,300.
We'll say 1,300. Okay. So this is my data. Now, what we're interested in is the likelihood that a person would live or die if they went by helicopter versus going by road. We want to compare them to see whether or not one is better than the other. What's the probability that a person died given that they went by helicopter?
64 out of 200.
64 out of 200, which is 32%. So 32% of the patients died when they went by helicopter. And what's the likelihood that a patient died if they went by road?
260 over 1100.
260 over 1100, which is 23.63 bar percent, if I want to be really, really exact. Well, I don't know about you, but when I look at this data, it certainly seems that I am more likely to die if I go by helicopter. So I think I'd prefer the road, wouldn't you?
No.
Why not? That's what the math tells me.
It was just a comment, but yeah.
I'm sorry?
It was a dumb comment.
Wait, yours or mine?
The people in the helicopter are probably more likely to die already. Like their situation is more imminent. so-
Okay, so we're not really looking at everything here, because if they're going to go by helicopter, chances are it's a more serious situation. Agreed?
Yes.
And if it's a more serious situation, maybe that's the reason why the likelihood of dying is higher. So let's take the same data and divide it up. Let's look at the serious accidents: died, lived, helicopter, road. This is for the serious accidents, the major accidents. And when we do that, this is the data, 48, 60, 52, and 40. And then let's look at the same situation, died, lived, helicopter, road, for the less serious, I don't want to say not serious because every accident is serious, but the less serious accidents. And I get 16, 200, 84, and 800. So what's the probability that a person died by helicopter or road for the serious accidents? And for the died by road, again, for the serious accidents. What would the likelihood of dying if you go by helicopter be for the serious accidents?
$48 over 100.
Okay, 48 of 100, 48%. And how about dying by road for the serious accidents?
60 out of 100.
Okay, so that seems more like it, right? For the serious accidents, you're much more likely to die by going by road than you are to go by helicopter, correct?
Yes.
Okay, well, what about for the less serious? What's the likelihood of dying by going by helicopter here?
16 over 100.
Okay, 16%. And how about dying by going by road here?
20%.
20%. Again, seems reasonable. You're more likely to die by going by road than by helicopter. But this doesn't make any sense to me at all. I mean, it does because I know the answer, but it shouldn't make sense to you. Where are you more likely to die if it's a serious accident, helicopter or road?
Road.
Where are you more likely to die if it's a less serious accident, helicopter or road?
Road.
So in both situations, you're more likely to die if you go by road. Then why is it when I lump it all together, I'm more likely to die if I go by helicopter? All right, look at the numbers. This one's higher in the serious case, and this one's higher in the less serious case. Going by road certainly seems to have a higher mortality rate. And yet somehow, when we lump them all together, going by helicopter has a higher mortality rate.
Is it because in the general, like in the first graph that you, or the first box that you have, the people that lived have or I mean lived have a higher population?
Not exactly.
I feel like it has to do with the amount of people. Like, there's more people that go by road, so it kind of skews the numbers a bit compared to the lesser amount of people that take a helicopter.
Okay, so it certainly has to do with the numbers. I mean, it's not that less people have helicopters. I'm pretty sure if somebody were to get into a major accident, I think the hospitals themselves sometimes send out helicopters to pick people up for the more serious ones. I don't think it's always like, those people have their own helicopters. But first, before I answer it, Mando, you said it shouldn't be 40% instead of 20%. You mean the last case, 200 over 1,000? That's 20%.
Is that 800 or 300?
That's an 800.
Oh, I thought it's 300. My bad.
No, my handwriting. Mrs. Morris will be very sad. She'll take away my best penmanship at work that I won all those years ago. I was 7, so it's 38 years ago. Best penmanship. It's declined a little. My apologies. So,
You're good. You're
So-
good, I'm saying.
Oh, I appreciate it. So a few people did allude to the correct answer, which is that, and by the way, this is Simpsons Paradox. Okay, Simpsons Paradox is, and I'm going to read it word for word here. It says, an association or a comparison that holds for all of several groups can reverse direction when the data are combined to form a single group. This reversal is called Simpsons Paradox. And like most paradoxes, it doesn't hold up to scrutiny. It's a superficial misunderstanding, which is cleared up when you come to a deeper understanding of the situation. On tests, the only questions I've ever seen on tests, midterms, finals, etc., involving Simpsons paradox is along the lines of just explaining in words what it is. Like I've seen a multiple choice question. What is it called when something will reverse direction when you do this and this? And the answer is, well, central limit theorem, the law of large numbers, yada, 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 or Simpsons paradox. Like, oh, it's Simpsons paradox. That's all I've ever seen. So they don't really ask mathematical questions on it. It's just understanding it. But the idea, the reason why it works this way is because of the numbers. The total number of serious accidents here is 200. And the total number of less serious accidents here is 1,100. Which means when I look at these two numbers, the probability of dying due to helicopter in the first case and dying due to the helicopter in the second case, the numbers are not, so the average of 48% and 16% is exactly 32%, which is what we have up here. And it makes sense that it's the exact average because we took the 200 people and did 100 in this case and 100 in that case, which means they were exactly the same size groups, 100 and 100. So the average here and the average here, that should average to the number right in between, which is 32%. But when I look at the road ones, I get 60% for this one and 20% for this one. Now the average would be 40%, but look at the size of the second group relative to the first group. No, not those numbers. It's the total here is 1,000 and the total here is 100. It's 10 times the size. The 20% group is 10 times the size, which means the weighted average of 20 and 60 is shifted considerably towards the 20, which is why it ends up at 24% or so. It's much closer to 20 than to 60. And what happens therefore is not 40 right in between, but it shifts enough over that it goes past the 32%, which is the helicopter average, and therefore it reverses direction. But it doesn't really reverse direction. It's just weighted that way, so it seems like it reverses direction, which is again one of those situations where two different statisticians can come into two different results on the same data. One person might only look at that and say, helicopters are a waste of money. People die much more often, not much more, but 8%, 7% more often on helicopters. So let's not have them anymore. And then someone else will say, wait a second, let's analyze a little more deeply. And we see that, wait a second, helicopters will save lives in both cases. So this is Simpsons paradox. It's the idea of reversal of direction because of skewed sizes of population. Hopefully that made sense to some extent. Again, it's not something that is asked mathematically. I've never seen it asked mathematically as much as it will or could be asked conceptually. Now, I have seen the final, but I didn't really read every question, so I can't really tell you whether or not there will be a Simpsons paradox question on it. Are there any questions though on what we've done today so far, either two-way tables or Simpsons paradox? Going once.
Not for me, thank you.
Awesome. How about everyone else?
Thank you, Noel.
All right, I'm still looking at my emails here. I just took a look at glance at them. I still have people who I know are here because they signed in, or at least they said yes earlier, who have not taken the exam yesterday and have not emailed me. So I'm a little at a loss to understand why you would not do that. If you're actually going to keep attending classes in the hopes of doing well and passing, and then not emailing me about making up that test, please do it now. Anyway, with that being said, moving on to chapter 24. This is the very last chapter. 2 categorical variables. The chi-square test. If you want to be really adventurous, you could pronounce it the chi-square test, but then people just look at you funny because nobody really pronounces it that way, but that's the way it should be pronounced, the chi-square test. So we have z-tests, we have t-tests, and now if you look at your calculator and you go to distribution, after the normal, which is your z, and after the t stuff, you will see that, and that is the chi-square. So we have it on the calculator, chi-squared PDF, chi-squared CDF. And if you do stat tests, you have your z-test, your t-test, your sample test, your prop test, your intervals, your z-interval, your two-interval, your prop interval. And then afterwards, we have the chi-square test and the chi-squared GOF test. We're going to be using both of those for this chapter. This chapter is about the chi-square test. And it is the
Where is it
test.
located again, Professor? Sorry.
If I do what, I'm sorry?
Where was it located on the calculator?
Stat tests. After the intervals, we have the chi-square tests.
Oh, okay.
You have the chi-square test and the chi-square GOF test. The stuff afterwards we don't do. So we don't do the F test, we don't do the Lin-Reg tests, and we don't do any ANOVA in this class. So it's
Okay.
stops here. This is the last chapter. And what we're doing now is we're doing tests on two-way tables.
Bless you.
Woo. Save that guy for later. Okay, thank you. So let's do an example to illustrate this. And okay, this is on page 528. We have the following table. We have young adults whose ages are 19, 20, 21, and 22. So the first categorical variable is their age. And the second categorical variable is where they live. So some of them live with their parents or another home. So it says here another person's home. So I'll just say another home. Your own place. You got your own place in a group like a dormitory or maybe a shared house or well, you know what I'm talking about. And then we have other. So we have 4 possibilities for age, and we have 5 possibilities for living arrangements. And the question is, first, here's the data. Let's fill in the data. We have 324, 378, 337, 318, 37, 47, 40, 38, 116, 116, and then the next one is 279. And then we have 372, 487, and then 58, 60, 49, 25, 5, 2, 3, and 9. A sample survey asked a random sample of young adults, where do you live now? That is, where do you stay most often? This is a two-way table of the 2,984 results. This is on page 528. Okay. With me so far?
Yes.
Okay, now we can also write the totals down. They give us those. So this one is 1357. This is 162. This is 1254. This is 192. This is 19. And we get 540, 766, 801, and 877. How many joint distributions do we have here, by the way?
One.
One. How many marginal distributions do we have?
Two.
Two. And how many conditional distributions do we have?
9.
We have 9. Okay. So the question is, the first question we're going to ask is, or the question for this particular example is there a connection between the two categorical variables? Is there a relationship between them? The null hypothesis will always be no relationship. Will always be no relationship. And the alternative hypothesis will be there is some relationship. There is some relationship. The null hypothesis is always the no relationship one. And the alternative is always the there is some relationship one. So any relationship that you can find at all is going to make us reject the null hypothesis. Whereas if there's no relationship, then we do not reject the null hypothesis. So how do we attack a problem like this? And the answer is as follows. If there's no relationship at all, then the 1357 people who live with their parents should be spread evenly amongst the 4, correct? In some sense, right? Do you agree with that?
Yes.
But at the same time, the 540 19-year-olds should be spread evenly amongst the column. And the 162 in the home should be spread evenly, and the 766 and the 20 should be spread evenly, and the 21 and the 22 and the 1254 and the 192 and the 19. So the numbers should be probably different than the actual values that we actually have if there really is no relationship between them. So what we need to do is we need to compute, and the calculator will not do this for us, by the way. We need to compute the expected number in each column if the null hypothesis is true and there really is no relationship between them. So we need to make a second table of 5 rows and 4 columns. And we need to put in here what we expect if the null hypothesis were true. And the method of doing this is actually really straightforward. Let's start with the first entry, the 324. And the question is, what should that 324 be if the null hypothesis were true? So here's what you do. You take the 324 and you go to all the way to the right, the margin over there, and all the way down, the margin over there, and you multiply them. What do you get when you multiply those numbers? So multiply the 2 marginal values for the cell, the top left cell, 324. When you multiply 1357 and 540, what do you get?
732,780.
Correct. And now divide by the overall total, 2984. What do we get when we do that?
245.57.
Okay. So if the null hypothesis is correct, that cell should really be 245.57. What should the next cell be?
Can you please explain it one more time what we did?
Whatever cell you're looking at, you take the two numbers in the margins for that value, multiply them, and divide by the overall value.
Would it be 348.35?
348.35 is what I get as well. Unfortunately, for these types of problems, you need to compute it for every cell. You got to do it manually. Your calculator will not do it for you. So you should pick a cell. I'm going to write them all down just to have them. But you should pick a cell at random and make sure what you get is the same as what I got, or what I'm copying from the book, because I'm not actually doing it. Just pick one at random and confirm, or even do it a few times. Just confirm that you get exactly the same thing that I do. Did anyone get one that was not, or is anyone doing it and getting them that are? Write in chat whether you are or not, just so I have some idea that you're following.
I was able to get it.
I'm sorry?
I was able to get it.
You are getting it?
Yeah.
Okay. Anyone else?
Me too.
Same, good. Okay. So these are the values that we would expect to have if the null hypothesis was true. When you look at the values that we actually have and you compare it to the values that we actually expect, are they close or are they not close?
Most of them don't seem like they're very close. Like they're kind of off.
Yeah, most of them do seem a little off, right?
Yeah.
But are they off enough that we would reject the null hypothesis or not is the question. So what we're going to do, like we did for all the other tests, is we're going to compute a p-value, and we are going to compute a test statistic, and we're going to use the p-value or the test statistic to determine whether or not we're going to reject the null hypothesis or not reject the null hypothesis. In the case of the ones that we did before, the test statistic was always the same. Data minus the mean divided by the standard error. For all of our cases, that was the test statistic. Data point minus the mean divided by the standard error. This one's a little more complicated because there's not like one data point, and our null hypothesis doesn't have a mean, and there's no standard error. So the approach is very, very different. The chi-squared value is computed as follows. We take each observed outcome and we subtract the expected corresponding outcome, square that, divide by the expected outcome, and then add them all together. So our test statistic, our first test statistic, for example, not our first test statistic, we only have one test statistic. Our first value, what's our first observed value?
324.
324. What's the corresponding expected value?
245.57.
So we're going to subtract them, we're going to square that, and then we're going to divide that by 245.57. And I use the actual full decimal for full accuracy. But you go ahead and do it. Tell me what you get, approximately at least.
Is it 25?
I get 25.05. If you got a little off because you rounded, it's essentially the same thing. 25.05. Plus, and let's just do one more just for completeness. What was the second of my actual values?
378.
378. What was its corresponding expected value?
348.35.
348.35. So when you do observed minus expected, you square it and you divide by expected. What do you get in that case?
I got 2.52.
Yeah, I get 2.52 as well. And plus dot, 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 dot. We're not going to do them all. As you can see, it's a relatively long process to do this. The book did it for us, and they got a test statistic of 193.58. That happens to be what they got from the book. Okay, so this is the, I'm going to call this first one here the actual. And this down here, I'm going to call the expected. Now, if our expected values were in the vicinity of our actual values, what would all these numerators be approximately?
Zero?
They'd be pretty close to zero, right? If the
Yeah.
observed and the expected were in the same vicinity, the difference should be close to zero, which means we would expect to have a pretty small test statistic, a pretty small chi-square. Would you agree with that?
Yes.
So in general, small chi-squared values imply that the null will fly. Imply null will fly. Small chi-squared values imply the null hypothesis is correct, so the null will fly. Large chi-squared values imply the null will die. Of course, if you do it that way with the rhyming thing, it kind of makes the whole mnemonic thing tough. The question is 193.58 big enough for us to reject the null hypothesis in this scenario? So to do that, we will have to consult a chi-squared table. No, it's not what I want. Maybe this one. It's pretty small. Oh, that was pretty big. This chi-squared. Okay. So here we have a chi-squared table. And as you can see, in order to know which square to use on the chi-squared table, you have to provide two things. The left column, df, what do you think df stands for?
Degrees of freedom.
Degrees of freedom. So that's the first thing we got to figure out. Before we know which row to use, we have to know how many degrees of freedom there are. So what is the number of degrees of freedom in this case? So the answer is a nice simple formula. R minus 1 times C minus 1. Any questions on that?
What is R and what is C?
Those are two great questions. All right. What is R and what is C? If you're not asking that just now, you are not paying attention. What do you think R and C are? Think about it. Here's my table. What do you think R and C might be? I want to see if this is intuitive or not. I mean, I know the answer. To me, it's like, oh, it's obvious because I know the answer already. But what do you think R and C might be? They have to be numbers. R minus 1, right? You can't subtract 1 from like a banana. So R and C have to be numbers. What do you think they stand for?
I think the R is the total of the actual.
Why would I use the letter R for that?
I'm not sure, but the degrees of
Reality.
freedom in general is the n minus 1, so which is n, which is a number of the sample size. So I'm going based off on that.
Okay, fair enough. So I'm going to give you a little hint. R and C stand for words that begin with R and C.
Does R stand for results?
Nope, but that was a good guess.
Ratio.
Nope. We have a column and we have rows. R is the number of rows and C is the number of columns. So how many rows do I have in my table? How many rows do I have in my table?
5.
5. How many columns?
4.
4. So in our case, we get 5 minus 1, 4 minus 1. So 4 times 3. This particular situation has 12 degrees of freedom. Number of rows of minus 1, number of columns minus 1. So if I go back to that, if I go back to the table, I now know which row to use. The degrees of freedom is 12 rows, and I'm going to look for my test statistic. What did I get again? 193.58. Where is it? Where's my test statistic for degrees of freedom 12?
What's our p-value?
Well, the p-value comes after you know your test statistic. The p-value is the likelihood of being past your test statistic. So I can't compute my p-value until I know my test statistic. I mean, they're connected, obviously, right? If I know my test statistic, I know my p-value. If I know my p-value, I know my test statistic. So where is my test statistic so I can calculate my p-value? Where is it? 12. I'm looking at the row with 12. I don't see it. Where is it?
Is it too high then?
It's way off the chart. The last column for the p-value is 0.001. And I'm not even close to my test statistic. So my p-value is much less than 0.001. Now, what does a p-value that small tell me?
You reject the null hypothesis.
We reject the null hypothesis. And therefore, there is some connection between them. Now, I'm not giving you again any theory for why this approach works. I'm not providing that at all. I'm just giving you the approach. Does the approach make sense?
Yes.
Yes, we all agree the approach makes sense. Caught in 4K, yes.
I meant to send that like a long time ago when the picture of the man came up on your screen, but I totally forgot to send it, and I just put yes.
Okay. I'm like, I'm not following this one. I mean, I know I'm not, hip with this generation and whatnot, but what the hell is she talking about? Okay. So this is the idea for essentially the entire chapter. We're going to see a couple different scenarios, but all of them are going to be similar to this. So before we go on, just in general, when can I use the chi-square test we just developed? Are there any requirements like there have been in the past with an SRS? It's normal, and it's this, it's that, and the counts are this big, and 10 successes, 10 failures. I mean, what do we need here? So the answer is yes. We have a couple of requirements. First, no cell can have 0, can have an expected count of 0, which really makes sense because if you look at the formula, we divide by the expected value of each cell. If it's 0, how are you going to divide by 0? So no cell can have an expected count of 0. At least 80% of cells are above a count of 5, above or equal, really. So I'll say above a count of 4, i.e. must be 5 or more. Yeah, that's it. Those are the two. No cell can have an expected count of 0, and at least 80% of cells are above a count of 4, i.e. must be 5 or more. In that case, you can use this technique. Now, how are you going to do it on your calculator? So let me show you how to do it on your calculator. If you go to stat and you go to tests and you go down to the chi-square test, you get to this point right here. You should all get to this point right here, where it says observed A and expected is B. What are those A and B's? Anyone know what the A and B's are?
Are they tables?
I'm sorry?
Tables?
Well, they are a table in a sense, but we don't really use tables in math. You know what we use instead? What kind of looks like a table, but is not really a table? Anyone know? We use a matrix. Has anyone here ever done matrices?
Yeah.
So on your calculator, you'll see in the first column halfway down in blue, or whatever color your calculator is, you'll see the word matrix. So go hit matrix, and you should see something that looks like this. Do you see it?
Hey, where do we go for that?
In the first column, you see the word matrix? On the left, halfway down?
That wasn't the stats.
No. On the calculator, in the first column, the button that says matrix. Do you see the word matrix on the front of your calculator? It's not in stats. On the front of the calculator, the word matrix.
So you hit,
Oh, yeah,
you hit
no, I see it.
second M matrix, right? Yeah.
Say again, second matrix. You see it?
Yeah.
Yeah.
So go second matrix and then go over to edit and pick a matrix. I picked A. And I want you to put in the actual values. 324, 3. This is a 5x4 matrix. We're putting in the actual values. And alas, this particular technique just is time consuming. But when you're done, your matrix should look like this. And while you're doing, well, actually, I have to make sure that I'm not going to be locked in here. I'm going to tell you how to do the second matrix. So do you all have your first matrix done yet? Matrix A?
Not yet.
Okay? You guys with me or no?
Yeah.
Okay, now hit second matrix again. Go to edit. This time pick matrix B. And again, make it a 4x4 matrix. I mean, a 5x4 matrix. I'm sorry, 5 rows, 4 columns. And here's what I want you to put in the first entry. Don't put in 245.57. That's an approximation. Why use an approximation if we don't have to? Actually put in 1357 times 540 divided by 2984. What does the entry turn into when you do that?
When I'm trying to do the second matrix, it tells me error undefined.
What do you mean? Walk me through exactly what you're doing, please.
I just put second matrix and then I try going to B.
Did you go to edit?
Oh, okay, there you go.
It's important to do this at least once. So that's why I'm walking you through it. Seems a little bit like a waste of time, but it's really important to know how to do this. So just one time.
It's giving me the same values.
What are you typing in exactly?
I'm putting the 1357 times 540 divided by the 2984.
Okay, that's for the first one. Now, what do you do for the second one?
I haven't done the second one yet.
Well, what do you mean the same values? Because that's only one time, right?
Oh, like it's giving me the 245.57 on the calculator.
That we got earlier, you mean this one?
Yeah.
Yeah, of course. Oh, it's the same as, you mean it's the same as the one that we got that you're supposed to have?
Yeah. So should I just
Gotcha.
copy that table, second table?
Yeah, well,
Okay.
no, that's what I'm trying to say. Do it this way so that you're not rounding.
Okay.
I want to be as accurate as possible across the board. So do it this way. I just got to check to make sure they're not going to lock me in, that they have to clean. So just give me a second. I'll be right back. But please finish your matrix B. I'll be right back. Are you guys talking? Did you guys clear up whatever needed to be cleared up?
Yes.
Okay, so I finished my second matrix and I have this. Hopefully you guys have something similar. Tell me when you're done, please.
Professor, what value did you get for this first column, second row?
First column, 29.316.
Yeah, same.
Thank you. Sorry again. All right. So when you do that, guys, just quickly, now go to stat, tests, chi-square test. And you have your observed as your A, expected as your B, and you calculate. What does it give you for your chi-squared? What does it give you for your degrees of freedom? And more importantly, what does it give you for your p-value?
For the chi-square, it gives you 193.54.
Which is essentially what we had from the book, right?
Yeah,
And what is your degrees of freedom?
I have 6.98.
No, the third column, degrees of freedom,
Sorry, 12.
12, which is what we got as well. And what's your p-value?
Like 6.98 to the negative 35.
Right, that's a pretty unlikely situation, right? A p-value that small.
Yes.
So this again lends, I mean, it agrees with what we had, that the p-value was much less than 0.001, right?
Yes.
Okay, I gotta go because they're locking up. So we will end here. We will finish chapter 25 on Tuesday. It will not take us very long. And then we will do a little review for Tuesday and Thursday, or the remaining part of Tuesday and Thursday. Again, if you did not take the test yesterday for whatever reason, I'm asking again, please, please, please email me. I still see in this class right now, at least one person who I know didn't take it, who has not emailed me. I don't know what's going on there, but if you want to take it, contact me. Otherwise, I really can't do much. So otherwise, I will. Where'd everyone go? Hold on. There's only 15 people in the room right now.
Yes.
Wow.
There was about like 22, 20, I think when you said that we're done, I think people started to leave.
Wow.
Yeah, there was 21, 22.
I should do attendance again, but I'm too tired. Okay. Well, anyway, if you haven't done the evaluation, please do it. And I will see you guys. Have a good weekend. I'll put the homework up and I'll see you guys on Tuesday.
Okay. Thank you.
Thank you, Professor.
You're welcome, guys. Take care.
Good
Everyone. Okay. Bye. Thank
Have
you.
a good night.
You too.
Oh, good one, Professor.
You too, guys. Okay.
Professor, I have
Yeah.
a question.
Yeah.
So if we send you an email like about like a time that we could take the test, will we get like a confirmation like on when we're gonna actually have like the time where we're supposed to come in, if that
Yeah.
makes sense?
Yeah, I'll confirm it with you. I gotta talk to the math department to make sure it's okay, but I'll confirm it with you.
Okay, thank you.
Okay, I gotta go. Okay, bye. Bye.